studios of Way Happy. This is Mr. Meyer and the fundamental theorem of calculus. How awesome is that? I mean, this is the fundamental theorem of calculus, and we're going to talk about it. So, you know that Newton and Leibniz had so much to do. Well, their teacher was Isaac Barrow, and Isaac Barrow was the guy who discovered that in calculus, the relationship between differentiation and integration were inverses, just like multiplication and division are inverses. He's like, hey, look, these things are inverses of each other. So super cool. And then he found out this beautiful equation here that you can now see. He told us that if you have the integral, now look, it's a definite integral because it's going from A to B, then you can integrate that, find, like the antiderivative and evaluate it from A to B. And the way you evaluate that is you plug B into the antiderivative and you subtract A that was plugged into the antiderivative. And that is the fundamental theorem of calculus that will give us the net change, right? That not the area, so we have to be careful, but it'll give us the net change. So there you go, the fundamental theorem of calculus, and let's use it because finding derivatives or anti-deriving is super fun. So see this integral here. I can either, to find this integral, I can find the area under the curve using the LRAM, RRAM, mid-MRAM, or trapezoids, or now, thanks to Barrow, I can figure out what this is. So first, let's go in and anti-derive this. So if I'm going to find the antiderivative, e to the x is just e to the x, and 3 is minus 3x, and plus c, but this is a definite integral, so we don't need the plus c, but I'm going to put it now just to show you why you don't need it. So there it is. That is our integral, right? That is me anti-deriving, and I'm going to evaluate this from 3 to 1. So what does that mean? That means I'm going to plug in a 1, or plug in a 3, and I'm going to plug in a 1, and I'm going to subtract those two things. So e cubed minus 9 plus c, all of that is when you plug in a 3, minus, now plug in a 1, e to the first minus 3 plus c, and you might already notice what will happen to our good friend c, the constant. Distribute that negative all the way through and combine like terms, which I don't think I have much of except for the 9 and the 3, and I guess the c's. I will have e cubed, and then I see a minus a e to the first, and then I have a negative 9 minus a negative 3, so negative 9 plus 3 is minus 6, and then the c's cancel, and that's the whole reason you don't have to put the plus c on these definite integrals. And there's my answer. There's an exact answer for the area under the curve. Now, you can think, is that actually the area under the curve? Is there any part of this graph that is maybe in negative territory, and that's why it's getting us a net change? Or is all of this above the x-axis and we're getting the actual area? So it might be something to think about. What does e to the x graph look like? It's a growth graph. It's picked down 3. So, and it's evaluated from 1 to 3. So I'd want to look at a graph or think about that graph and see if I'm getting area or not. All right, what about the next one? Might want to clean that up a little bit. I don't like the 2 on top because it's a constant. So I could pull that 2 out front and have the integral from 0 to a half of 1 over the square root of 1 minus x squared dx. Now I really wish I knew what the antiderivative of that. Wait a minute. That's one of those inverse trigs, isn't it? Yeah, that's totally arc sine. Oh, this is beautiful. So take the antiderivative of that. It would be 2. I'm going to leave that 2 on the outside. I'm going to have arc sine of x. And I got to evaluate that from 0 to a half. All right. So I can plug that in. And I'm just going to leave the 2 out here until I'm done. So the arc sine of a half. So I'm going to use my fingers. I'm going to pull down the arc sine of a half. That is pi over 6. And arc sine of 0 is don't need the parentheses here because there's nothing to distribute. Arc sine of 0 is 0. And so if I figure out that is pi over 3. And there you go. There is the exact integral, definite integral from 0 to a half. See, these things can be way too darn fun. All right, what about the next one? Let's try that. I see I want to integrate from 1 to e squared. Okay, that's kind of weird. Of 1 over x, right? So integrate from 1 to e squared of 1 over x dx. Now you know the antiderivative of that one. hopefully you're not saying e to the 0. Hopefully you're saying, oh, no, that is natural log. So if I do take the derivative of that, I have the natural log of the absolute value of x. And I'm going to evaluate that from 1 to e squared. And then if those things are positive, we can drop the absolute value bars, which I think we're going to feel pretty safe here. When I plug in the e squared, I'm going to have ln of e squared. Now, that e squared is a positive number, so absolute value is redundant. So that's why I don't have the absolute value bars around it. And now I'm going to subtract, and I'm going to plug in 1, and 1's positive. So it's going to be ln of 1, which, by the way, at this point, you have numerical answers. College Board says, hey, you're good. Stop. Right? You have to get to that step. And these have to be numerical. They can't be like undefined or something, but you can be like, yeah, they are something. I just don't know what they are. But we can continue on. We can go, all right, let's see, what is that? Well, if we all know our properties of logs, we know that that is going to turn into 2. And ln of 1, remember the 2 came out in front, and ln and e are inverses, so they turn into 1. 1 times 2 is 2. And what's the natural log of 1? Well, remember, logs mean what exponent would you put on e to get a 1? Well, that would be 0. And so there is our area. Well, maybe it might be our net area. I'd again have to look at the graph. Well, wait, I know what 1 over x looks like. 1 over x goes like this, right? And if you're going from 1 to e squared, here's 1, here's e squared. Yeah, that's going to be the area. So that's kind of nice to think about. All right. That's the bell. I will get back to you after a break and ask you a question, and then we'll finish example 2. All right, have a great day. All right, nice work there. Now let's go ahead and finish this up. Let's go ahead and try another one, or another 4. Let's evaluate using any method. Any method, huh? All right, well, what do you mean by any method? I think we only know one method. Not true, we know 2 methods, right? We know one method to evaluate an integral would be to use to find the area under using rectangles, using LRAM, RRAM, MRAM, trapezoid rule, or any other way, using geometry, really. And then the other way would be to integrate using the fundamental theorem of calculus. So let's see, the first one, I would look at it and say, you know what, I probably could take that derivative pretty easily. And so I think I will, and I will use the fundamental theorem of calculus. So if I'm going to go ahead and integrate this, I'm going to go up to x cubed, and I'm going to divide it by 3. So how about 1/3 x cubed? And I'm going to bring that up to x to the first and divide by 1, so minus 3x. And that is something that I will evaluate from 1 to 2. Notice I didn't do the plus c because you guys know it's going to cancel out, right? So let's see, if I plug in a 2, I get 8/3 minus 6 is the first term. And then minus, now we got to plug in the 1, that would be 1/3 minus 3. And I guess I can somehow put these all together. I kind of see 8/3 minus 1/3 is 7/3. And I see negative 6 minus a negative 3, so plus 3 minus 3. And then I guess I could make that, 9/3? So 7 minus 9/3. 7/3 minus 9/3 is negative 2/3. And lo and behold, I have the area. Now, what does that mean? Does that mean the area is all below the x-axis? No, it means it probably cancels out, right? And that's the net accumulation of the areas. Because, well, yeah, look at that. It's a parabola. It's down 3s, or, some of it is below. So kind of nice to think about the areas once in a while. All right, what about the next one? I see a 3 out front. I'm gonna pull that 3 out front just because it's annoying, and make this x to the half dx. Again, probably going to use the fundamental theorem of calculus. So got to go up a power, x to the 3/2, and I got to divide by 3/2 or multiply by 2/3. And don't forget there was a 3 out front of that. And with all of that, you got to evaluate that from, what did I say, 1 to 4? All right, sounds good. The 3's cancel, so really, what is this? This is 2x to the 3/2 from 1 to 4, if you want to clean that up a little bit. So let's see, let's plug in 4. Now I'm going to do the square rooting, right? The 4 to the 3/2, that is the square root of 4 cubed, or the square root of 4 and then cube it. And I'm going to do that. I'm going to do the square root of 4 first because that's 2, and then I'm going to cube it. So it's going to be, if I plug in 4, I'm going to get 2 cubed is 8 times 2 is 16. And then I'm going to plug in 1, which is 1 cubed is 1 times 2 is 2 minus 2 is 14. And there's my answer. Again, the area, oh, it's a square root shooting star. So yeah.